Hello students! This lesson is on modeling with functions. You can afford 1,200 feet of fencing and you want to build a divided rectangular enclosure against an existing wall. Express the total area of the enclosure as a function of the length of one vertical segment. So we have an existing wall that does not require any materials for us to build our enclosure. So the 1,200 feet of fencing that I plan to buy needs to be used to make these three sides and then this side as well. Now we want to express the total area as a function of the length of one vertical segment. I'll use capital A for the total area and x as the length of one vertical segment. So in my picture, this will be x, this will be x, and this will be x. They must all be the same. The other length doesn't necessarily need to be x, so we need a new letter. I use L for length. Now the area of the entire enclosure would be the area of this pen plus the area of this pen, which we can calculate by simply doing this width times this length. So we have x times L. So currently we have two variables in our area formula. We want to narrow this down to only one variable, and that being x. This is where the 1,200 feet of fencing comes into play. So if I add the three x's plus the one L, that should account for all of the fencing material I have. So the sum of these four lengths should equal 1,200, which means that 3x plus L should be 1,200. I can take this equation and solve it for L by subtracting the 3x, and then I can substitute this expression in for this L in my area formula. So this gives me area is equal to x times, and then 1,200 minus 3x. So now I've accomplished my goal of expressing area as a function of x. So in more formal notation, it would read a of x equals x times 1,200 minus 3x. Now I'll distribute this x and reorder the terms. We recognize now that this is a quadratic function with a negative leading coefficient. So I do expect a shape, when graphed, to be an upside-down parabola. And here is general form, and here is a factored form, the form I started with. So we've accomplished our goal so far, and I've written it in two different forms. Now without technology, graph the function above and find the dimensions of the enclosure that maximize the total enclosed area. Give this maximum area. So this is a quadratic function that we can graph by finding its x-intercepts and its vertex. I'll begin by finding the x-intercepts, and I'll use factored form. Since it's factored, I can set each factor equal to 0 separately, and that gives me two answers, 0, and then the other answer is 400. So I'll create an x-axis, put my two x-intercepts on there, and I know that the axis of symmetry, it will occur when x is 200. So to find the vertical coordinate, and keep in mind the vertical axis here is area, because we are graphing an area function as a function of x. So the vertical component is found by plugging this red 200 into the area function, and I will use this factored form to do so. So we have 200 times 1,200 minus 3 times 200. This gives me 200 times 3 times 200 is 600, removed from 1,200 is 600, which gives me 120,000. And this would be measured in square feet, giving us this vertex. This is the point that has maximum area, in other words, the highest point. So our dimensions should be, x should be 200 feet. And then let's calculate what the length is by plugging 200 into this L function, and we get the L should be 600, and that's measured also in feet. And then the max area is 120,000 square feet. Notice I had already calculated the 600 right here and getting the 600 feet for the length. That's because our structure was, the 200 was an x, and this calculation was my L, and x times L gives me area. I could have also found the vertex using the general form right here by using the formula x equals negative b over 2a, where b is the 1,200 and a is the negative 3 lead coefficient. So we get negative 1,200 divided by negative 6. That confirms the 200 value for x that I got over here by using symmetry, by knowing it had to be halfway in between the two x-intercepts. So it's very fascinating that when we model this rectangular enclosure as a function of x, that winds up producing a function that is a quadratic function that has a maximum output. Okay, let's go to the next page. You must design a box with no top, a square base, and a volume of 10 cubic feet. The base of the box costs $3 per square foot, and the sides cost $2 per square foot. Express the cost to make the box as a function of the width of the base. So cost will be our function. I'll use a capital C for cost, and we want it to be a function of the width of the base. Let's go ahead and just use x again as our input variable. So in this drawing, we know that the width of the base needs to be x, measured in feet. We are also told that the base is square. So that means the other dimension of the base should also be x. However, the height we don't know. I'll use h. The base is a square that is x by x, and it costs $3 per square foot. And then each side, if you pull the box apart, would be X by H, and it costs only $2 per square foot. So C will be the total cost. You take the 3, which is measured in dollars per square foot, and multiply it by the area of the base, which is measured in square feet, and this is the cost for the base. To this, we want to add the cost for the sides. Well, the sides cost $2 per square foot. Area of each side is X times H, and that's measured in square feet. But then there are 4 of these, so we must quadruple this price. Now you can see in the arithmetic of units that the feet squares will cancel, leaving just dollar signs. So this function outputs a total cost measured in dollars. We'll now rewrite it without all the units. So we would have 3x squared plus, and then we'll have an 8xh. So our cost is a function of 2 variables, x and h. We want this to be a function of only x. This is where this volume information will come into play, because we know that the volume of the box, you would multiply the length of the base, the width of the base, times the height of the box, multiply those 3 dimensions, and you get its volume, which would be x squared times h. Now the volume must be 10 cubic feet. So whatever x and h are, this must be a true statement. We can solve this for h. H therefore must be 10 divided by x squared. And now I can do a substitution. This expression for h can go in for this h right here in my cost function. And so cost will now be a function of x, and it will be 3x squared plus 8x times 10 over x squared. And now I'll simplify this. 8 times 10 is 80, and then x divided by x squared will leave a x in the denominator. This is a rational function. I could get a common denominator and combine these terms into one fraction, or I could leave it just like this, because our instructions say next to use technology to graph the function and find the dimensions of the box that minimize the cost of the material needed to make the box. So we want to find x so that C, cost, is a minimum. Let's take a look at this graph. And this is what I see. We change my scale a little bit, and we see a rational function that appears to have some sort of parabolic asymptote. But we don't need to analyze too much. We just need to look into this region where the x's are positive. Keep in mind that x is a length, and so we don't need x to be negative in this scenario. So the only thing that matters is this portion of the graph that's here in the first quadrant. If you click on the graph, Desmos will automatically find minimums and maximums, and we can see that if x is about 2.37, then we'll have a minimum cost of about 50.61. So in my notes, I'll make a little drawing of this. It doesn't have to be exact. This is my cost function, and that minimum point was at approximately 2.37, 50.61. Now this first coordinate was an x coordinate, and the second coordinate was a c coordinate for cost. So x needs to be about 2.37 feet. We are asked to give the dimensions of the box, which are the length and the width of the base and the height. So this first value is that width or length of the base. Keep in mind that the base was square in this problem. We do need to calculate the height. We know that the height can be found by doing 10 divided by x squared, and we substitute this value, 2.37, into this height function. I'm going to call my x the variable a and store it over here and write as many digits as possible so I don't lose precision. So a is 2.37126, revealing as many digits as I can, and h is 10 divided by that value. So I can just say a squared there, and this calculates h for me with some precision. And now I will round this to the nearest hundredth, or 2 decimal places, so about 1.78. And this is the height of the box. So I have my dimensions. Now I just need to also give that minimum cost. And that's what this second coordinate is. It's a cost coordinate. And it's about 50.61 measured in dollars. And here are my answers for this problem. Any other choice of x I could have made would have led to a point on my cost graph that is higher than the minimum. So in other words, they would have been more expensive to make. Okay, let's go to the next page. A 6-foot tall painting is hanging on a wall, and the bottom of the painting is 1 foot above eye level of an observer. Express the angle theta in the image below as a function of the distance the observer is from the wall. So one variable is already identified for us, but this distance, let's use this as our input variable x. So I need to express theta as a function of x. And in this picture, x is the horizontal distance the person's eyes are from the wall, we'll say. Make a right triangle here with the wall. And this here is our painting that's up on the wall. We are told that it is 6 feet tall and that the bottom of the painting is 1 foot above eye level. Now in this drawing, this triangle right here is not a right triangle. However, This triangle is a right triangle, as is this big triangle. So focusing on those two triangles, we have an angle here that I'll call alpha, and then a big angle here we'll call beta. And the angle theta that I'm after is going to be the difference beta minus alpha. Okay, so here's a formula for calculating theta, but we need this to be a function of x. So focusing on alpha, we have a right triangle with an angle alpha here, and we know that the height of this triangle would be 1, and the adjacent or base of the triangle will be this x variable, which is how far the person is from the wall. This tells me that the tangent of alpha is equal to opposite over adjacent. So in other words, alpha can be found by doing the arctangent of 1 over x. Now, in this picture, these three angles, alpha, beta, and theta, are all acute. So arctangent will give me a correct angle here. I don't need to adjust it to put it into a different quadrant. Now focus on the big right triangle, whose opposite side would be 6 plus 1, or 7 feet. The adjacent would be x, and the interior angle here was beta. We know that tangent of beta would be opposite 7 divided by adjacent x. In other words, beta can be expressed as the arctangent of 7 over x. Now I can come back to my theta equation and say that theta therefore is the arctangent of 7 over x, and then minus alpha, which is the arctangent of 1 over x. And here now we have theta as a function of x. Now use technology to graph this function and to find how far from the wall the observer should stand to maximize how much the painting occupies their field of vision. Give this maximum angle. Now for the sake of understanding what's going on here, if this person moves closer to the wall, you can see how that red angle theta changes. Notice the angle begin to shrink to the point where the painting cannot occupy much of their field of vision, even if looking straight up. But as the person backs away from the wall, observe what's happening to that red angle. It got big for a moment and then begins to shrink again. So somewhere in this process, the angle will be as large as possible, thus the painting will occupy the largest amount of space in their field of view. We're trying to figure out how far this person should be so that theta is maximized. You can enter a theta by typing in the word theta, then make it a function of x, and then type in our function. I'll use arctan for the inverse tan, and we had arctan of 7 over x minus arctan of 1 over x, changing our scale a little bit. Notice that it does appear that as x goes to infinity, that theta is decreasing perhaps to 0. Because the further a person backs up from the painting, the smaller theta will become, meaning that the painting is occupying less and less space in their field of vision. We don't need to worry about negative x values here, but notice that we do have a maximum output here. When x is about 2.65, then the max theta will be about 0.848. In our settings, we are in radian mode, so that's how we are interpreting this output. It's an angle in radians. Switch to degrees will require us to change our vertical scale, that if the observer stands 2.65 feet away from the wall roughly, that the maximum angle in degrees would be about 48.6 degrees. So drawing this graph here doesn't have to be perfectly to scale. We have our graph, our x-axis, our vertical axis, which is a theta axis, and we had a maximum at approximately 2.65, 0.848. This is a theta coordinate measured in radians, and the first coordinate is an x-coordinate measured in feet. So the observer should stand approximately x equals 2.65 feet from the wall, and this will give us a max angle of about 0.848 radians, which was about 48.59 degrees. Okay, next slide. The function in the image below is y equals square root of x. That is this graph. Express the distance between the 2 points in the image as a function of x. So you have one point that's on the y with variable components, meaning you want to be able to imagine this point shifting around on the curve, and the other point is at the point 4, -1. So imagine this point moving around the curve, and then imagine the distance between the point on the curve and the point 4, -1. And our goal is to find a function that models this distance as a function of x, where x is the x-coordinate of this variable point. Okay, so let's draw a static version of this. Draw that diagonal line segment that connects the 2 points. We'll say this has a length L, gives us the distance between the 2 points. And then imagine a right triangle. Let's call these sides A and B. We know that by the Pythagorean theorem, and this is a right triangle, that a squared plus b squared would equal L squared. In other words, that L would be the square root of a squared plus b squared. Now make sure you do not simplify this to a plus b. You cannot square root a sum by square rooting the two addends. Well, how long is a and b? We can find a horizontal length between 2 points by subtracting the x-coordinates. This x-coordinate and then minus the variable x-coordinate. And we can find how long a is by doing this y-coordinate minus that y-coordinate. So a can be written as y minus -1, which is y plus 1. So I can rewrite my L function as the square root of, and then a is y plus 1, and that needs to be squared, and then plus, and then b is 4 minus x, that needs to be squared. So L is currently a function of two variables, y and x. But now I can use the fact that y is the same thing as the square root of x, if in fact this point is to be on the curve. So using that substitution, I can now say that L is equal to the square root of, and change y to square root of x, and then plus 1, and that's being squared, and then plus, and no need to change this second part. And now we have L is in fact a function of x, accomplishing our first task. Now use technology to graph the function above and to find the point on the curve closest to the point, referring to the point 4, -1. Give this minimum distance. Now I'm using a tool that you don't need to know how to create. Visually, I can see that the minimum distance is going to be probably somewhere in this area right in here, meaning that I expect an x-coordinate probably near x being 3. This length function or distance function has been entered in, and then here is its graph. The outputs of this function are lengths of the green line segment from the previous image, and we see that there's a minimum output occurring when x is about 3.22, and then a minimum output of about 2.9. Moving that data into a picture here, that minimum point is somewhere in here. We also see a y-intercept of a little more than 4. The rest of these details aren't as important. So our x-axis here is our traditional x, but our vertical axis in this picture is this L function. So this first coordinate is an x-coordinate, and the second coordinate is an L-coordinate, representing this length. And the length of that green line segment will be minimized when x is 3.22. And we don't have units on these numbers, so we'll leave it unitless, or just say units. And that min distance is L, approximately 2.9 units. Now this did say to find the point on the curve, and so far I've only found the x-coordinate. I haven't found the y-coordinate of it. But we know that y is equal to the square root of x in order to be on this curve in the first place. So we simply need to plug in this x-coordinate into this function. And I'll plug in a more precise version. So in this picture here, the closest point is approximately 3.22, 1.79. Summarizing down here. So here's an answer for finding the closest point on the curve. And then here's the answer for how far that point on the curve is from the point 4, -1. Now it can be helpful in this context to graph everything simultaneously. So the green is our L function. Here's our square root function. Here's our point in question, 4, -1. Here's a point on the curve and our line segment and a point on the green curve. I'll drag this point to 0 and then hit play. The green line segment shrinks in length to a minimum and then begins to grow in length again, as revealed by the outputs of the green graph. And we are minimized when we have an x-coordinate that was about 3.22142. And notice the y-coordinate on our orange graph, about 1.79. But the output coordinate on the green graph, the 2.9, is the length of that dashed line segment. That length is minimized, therefore the orange point is the point on the curve y equals square root of x that's closest to the point 4, -1. Okay, let's move on. A city can sustain no more than 4 million people. In the year 2003, which we'll say is t equals 3 years, the population was 2 million. Find two different functions that model the growth of the population in the general way shown below. Confirm with technology. This first coordinate, 3, stands for how many years after 2000. So that corresponds to the year 2003. And this second coordinate is the population measured in millions. Now this city can sustain no more than 4 million people. So notice we have a growing curve, but it's approaching an asymptote. That asymptote would be the max number of people that the city can sustain. So this line would be y equals 4 to represent 4 million people. Okay, we're going to do this in two different ways, although there are more. But let's begin by trying to find some sort of curve that follows a horizontal asymptote to the right, and then we'll transform that curve to match this data. For example, let's begin with a function 1 over x. Now 1 over x has this shape. It does follow an asymptote off to the right, so this will be a useful function to use. It also contains the point 1, 1, which will be helpful to track as we do transformations. Well, the curve that we want needs to follow the asymptote from below. So the first thing I want to do to this function is its negative to reflect the graph across the x-axis. And I'm only going to draw this portion of the curve. Now this goes through 1, negative 1. So this gap between asymptote and point is 1 unit. But in our image, this gap here between 2 and 4 is 2 units. So I want to do a vertical stretch next by multiplying the function by 2 and writing negative 2 over x. This gives me a graph that goes through 1, negative 2. So I have the correct distance between asymptote and that point. Now I need to do some shifting to move this point to this new location. I want to go right 2 units. To do that, I need to change x, or replace x, with x minus 2. That'll move our point in question to the location 3, negative 2, and still preserve that distance 2 from point to asymptote. And now I want to go up 4 in order to move this point from a height of negative 2 to a height of 2. That will also move the asymptote to the correct location, to a height of 4. So my final result is this function here, which we will confirm with technology. So I have my asymptote and my point. We begin with the graph of 1 over x, reflect it, stretch it by a factor of 2. Notice we have a point at 1, negative 2, and now we're going to shift right 2 and up 4. So shift right 2 by changing x to x minus 2. Now notice where that point is, and now we need to go up 4 by putting plus 4 at the end of this. And then sure enough, we wind up with a curve that passes through 3, 2, and then increases towards that horizontal asymptote at y equals 4. Let's do this again, but with a different parent function. Another function that follows the x-axis as an asymptote are exponential functions, and I'll use e to the x as my parent. However, the graph of e to the x is a growing exponential like this, passing through 0, 1. It follows the x-axis, but in the wrong direction. So the first thing I'm going to do is do a reflection about the y-axis by changing x to negative x. This will still pass through 0, 1, but it will now follow an asymptote off to the right like I want. Now we need to reflect this around the x-axis. So we're now going through 0, negative 1. Currently the gap between this point and the asymptote is 1 unit. I want that to be 2. So we need to do a vertical stretch again by multiplying this function by 2. That gives me that gap between asymptote and point of 2 units that I want. Now I need to do 2 shifts. I want to shift so that this point 0, negative 2 winds up being at this location 3, 2 instead. So I need to shift to the right 3 units and then up 4 units. And I'll do both those in the same time. So this gives me y is equal to, we have negative 2 e to the negative x, but change x to x minus 3. That shifts right 3. And then add 4 after the fact to go up 4. Notice my use of parentheses on the x minus 3. That's important. If you wanted to remove them, you can. You just need to distribute this negative. And so we can say a final answer of negative 2 e to the negative x plus 3, and then plus of 4. Let's confirm this one with technology. So I'll begin with the parent graph e to the x. Notice this point it's passing through. Going to reflect around the y-axis by changing x to negative x, and then reflect across the x-axis by putting a negative in front of the function as well. Now our point here is 1 unit below its asymptote. So we need to double the function so that I have a point that's now 2 units below its asymptote. And now we need to shift to the right 3 and then up 4. So where the x is, put parentheses and put x minus 3 in those parentheses. Notice where this point is now, and now shift up 4. And sure enough, we get a graph that passes through 3, 2 and approaches that horizontal asymptote, but this time using an exponential parent function. Okay, and this concludes our lesson on modeling with functions.